Welcome to this session on problem solving in asymmetric synthesis. Let us look into our first problem. Predict the major product in the following reaction. Let me take up the molecule. So as I work out the problem, you also can draw it in your notebook so that it will be easy for you to follow the steps. I have my molecule, my carbonyl compound. So we are trying to apply the Cram's rule and the Felkinand modification to compounds which has a prochiral carbon, and also a chiral carbon. So according to Cram's rule, we know that we need to draw our molecule in the desired conformation, and after that we have to perform the addition reaction. So the reaction conditions are you're using lithium aluminum hydride and diethyl ether at 35 degrees Celsius. Okay. So what is the product? Now, when we try to solve this problem, the first thing that we need to remember is we need to draw our structure or the conformation according to Cram's rule. So I'm drawing the structure according to Cram's rule. See, I'm actually drawing the structure in such a way that I view my molecule from this side. So when I view my molecule from this side, I will have my carbonyl oxygen at the top, tertiary butyl group at the bottom, and I will have my methyl group on my left hand side, my hydrogen in my right hand side, and then I will have my phenyl group. That's right. Okay. Now, what happens here? According to Cram's rule, when my carbonyl group is flanked between the medium and the small group, my nucleophile prefers to attack from the side of the smaller group. That leads to this product. So when hydride attacks the carbonyl carbon, my oxygen will be moved towards this side, so resulting in the formation of OH. The incoming nucleophile will be here, which is hydrogen. I have my tertiary butyl group at the bottom, and I am making no change to my molecule where I have my symmetric carbon. So I have my methyl here, I have my hydrogen here, and I have my phenyl here. Now in this molecule you can see my OH group is cis to my methyl, my hydrogen is cis to my hydrogen, and my phenyl is cis to my butyl. So how to draw or how to convert this Newman projection into a Sawhorse form? So when I try to convert this Newman projection into a Sawhorse form, I end up with a structure like this. I'm going to view the molecule from the chiral carbon side, and I will have my hydrogen here, I will have my methyl group here, I have my phenyl here, and on my other carbon I have my hydrogen here, I have my OH group here, and I have my tertiary butyl here. Okay, so you can see I've actually rotated this molecule, say I had rotated towards my right in an anti-clockwise direction. So when I rotate the molecule, I get this view of, or I get this view actually. So it's an equivalent structure. Now you can see my OH and methyl are eclipsing each other. My hydrides are eclipsing each other, and my tertiary butyl and phenyl are eclipsing each other. Now, what I do, I see we have just applied Cram's rule into this problem. Now let me add Felkinand model to this problem, because you can see here we have two bulky groups, and when there are two bulky groups eclipsing each other in a Cram's model, the relative conformation will not be stable, and that is where Felkinand modification comes into picture. So according to Felkinand modification, I have to put my phenyl group perpendicular to my carbonyl-carbon. So let me draw this first. Okay, so butyl. Now I have two possible conformation. So by my most stable conformation in this case would be now here I have drawn the most stable conformation. So what I have done is I have just rotated this phenyl group to this side. So my methyl group comes to the top. Okay, so it comes to the top, and my hydrogen goes here. Now, what we are trying to do here is we will try to do the addition from the side of the smaller group. So when I add hydrogen, I end up with this structure. Sorry. I have my OH group here. I have my hydrogen here. I have my tertiary butyl group here. And there is no change in the chiral carbon. I have my phenyl, I have my methyl, and I have my hydrogen. Now, how to correlate these two structures? Okay. Now, I will draw another structure. What I will do, I am going to do a 60-degree rotation, and I am going to make it as an eclipsed form. So when I do that, let me draw the chiral carbon first. I have my phenyl here. I have my methyl here. I have my hydrogen here. So I will be having the three groups here. So this will be my tertiary butyl group. So when I rotate this, my tertiary butyl group will be eclipsing my phenyl, and my OH hydroxyl group will be eclipsing my methyl. My hydrogen will be eclipsing my hydrogen. Now, if we could compare these two structures, oh my god, just compare these two structures. So I have my phenyl and tertiary butyl eclipsing each other, yes. I have my methyl and OH eclipsing each other, yes. I have my hydrogen and hydrogen eclipsing each other. Therefore, these two structures are same. So you get the same product when you apply the Cram's model and also the Felkin and model. So this is how we need to proceed whenever we get a problem using Cram's rule. Thank you for watching. So I have my starting material. The reaction is I'm using lithium aluminum hydride for the reduction of carbonyl group. I'm having a chiral center over here. So this is a chiral center in the molecule, and I end up with a product. I end up with a product. Okay, so this is my product. Now the options are: 1, we have to predict the stereochemistry of the product, and 2, the 1 is 3R 6S, 2 is 3S and 6S, 3 is 3R and 6R, and 4 is 3S and 6R. Now, how to proceed in this problem? Now let us take the help of Cram's model. So according to Cram's model, we know how to draw a Cram model, and in a Cram model we will have our medium group here, we will have our small group here, and we will have our large group here, and in this case our molecule has a methyl group. So when we try to draw the structure, again the respective groups, have my methyl here, I have my hydrogen here, and I have the largest group here. Now, according to the Cram's model, my nucleophile can come and attack from either side but the most preferred side is the attack from the side of the smaller group. Now when this attack takes place, I end up with a product like this. My OH will be here, my hydrogen will be here, my methyl group will be here, I have my methyl here, I have my hydrogen here, and I have my large group here, the side chain. Now if we look into the product, you can see that your methyl group over here and the large group, okay, your methyl group and large group are trans to each other. So they are trans to each other. Therefore, what we will do here is we will make a 180-degree rotation. We will convert this Newman projection into another form where we have our methyl group here and our OH group comes here and our hydrogen comes here. We have our methyl group here, we have our hydrogen here, and we have our large group here, right? So now this structure, so according to this structure, you can see our methyl group and our large group are anti to each other. You can see, so our methyl and large group are anti to each other, and our methyl and OH group are anti to each other. Okay, when the methyl and the large group are anti to each other, my OH and the methyl on the other carbon are anti to each other. So my OH and the methyl on the other carbon are anti to each other. In that case, this bond can be drawn like this. So this can be drawn like this, right? Okay. Now we have to see, we have to check the configuration of the isomer, and we need to number it from here. So I number it from here. Now now what we have done is, right now we have performed the Cram's rule and we have identified the product. From the product, we have identified the stereochemistry of the molecules or groups. Now we are numbering it. So let me number it as 1, 2, 3, 4, 5, 6 and 7. So after numbering it, so first thing I want to identify the stereochemistry of this third carbon. So when I take up the stereochemistry of my third carbon, I will say this is my group number 1 and this will be two, and I also have hydrogen here in this methyl group, so I have an hydrogen here because I have to draw that hydrogen in order to determine the stereochemistry of my product over here. Now if I take, so this will be number 2 and my methyl will be number 3. My methyl will be number 3 and you can see my hydrogen is pointing towards me. I move it in an anti-clockwise direction. So I have my 1, I have my 2, I have my 3. I move in an anti-clockwise direction, but my hydrogen is protruding towards me. Therefore, it is R. Therefore, I have my 3R. Okay. Now coming back to my carbon 6. So in my carbon 6, so this longest chain takes up the first priority. So I have priority number 1. My ethyl takes up the second priority, and my methyl takes up the third priority. I move in an anti-clockwise direction, but my hydrogen is moving away from me. So you can see the hydrogen is moving away from me. So I have my 1 here, I have my 2 here, I have my 3 here, but my hydrogen is moving away from me. Therefore, I can take it as yes. Therefore, it is 6 yes. Right. So the correct answer is 3R and 6S for this structure. Let us move on to another problem. Now, this problem we have to predict the product as well as the stereochemistry using Cram's rule. Let me draw the starting material. So we have a starting material here. My hydrogen, I have my methyl, I have my phenyl here. Next, now this reactant molecule undergoes a Grignard addition using methyl magnesium chloride. So you will get a product which is followed by a reaction with tosyl chloride in the presence of pyridine. And finally, we have to find out the stereochemistry of this product, and we have to identify which will be the major product. We have to apply Cram's rule, as you know. So we will take up the molecule, and we will try to apply the Cram's rule and predict the product. I will have my methyl here, my hydrogen here, my phenyl here. So I will have my methyl group attacking. Okay, so it will attack carbonyl-carbon, and I will end up with this molecule. I will have my OH here. So I will have my methyl here. I will have my hydrogen here. Here I will have my methyl, I will have my hydrogen, and I will have my phenyl. Now, if I could draw the structure in a Sawhorse form, you can see that the structure goes like this. So this is my Sawhorse form. I have my hydrogen here, I have my methyl here, I have my phenyl here. So I'm just trying to draw the Sawhorse form for this. Okay. Now on my opposite side, I will be having my methyl group here. I'll be having my OH here and my hydrogen here. Okay. Now, let me draw the hydrogen in a different way. Okay, so my hydrogen here. Okay. Now, this structure, this is my OH. Now this structure can be slightly modified to perform the second reaction, where I have to treat it with tricyl chloride followed by treatment with pyridine. So when I treat it with tricyl chloride, my molecule becomes like this. So after the treatment of tricyl chloride, so this is going to be my structure. So I have my methyl, I have my phenyl, I have my hydrogen here. I have just made a rotation here. Okay. Then I have let me have my tricyl group on the top to enable the elimination process. So I have my tricyl here at the top, I have my methyl here, I have my hydrogen here. Now in the presence of a base, the proton will be abstracted, resulting in the formation of an alkene, and my tricyl group will be pushed out. If that happens, I will end up with a product where I have my phenyl group and my methyl group, and if you closely look, you can see you have your methyl group and your hydrogen. Okay. Now, what is the stereochemistry of this product? Now, the stereochemistry of this product is E. So this is an E isomer. So if I am going to perform the reaction according to the Felkinan model, from the major product, I am going to get only an E isomer. How is this an E isomer? Because if you take this carbon, we have to give priority to the groups. So this gets priority number 1 and this gets priority number 2. Again, for this carbon, this gets priority number 1 and this gets priority number 2. The priority 1 and 1 are trans to each other, priority 2 and 2 are trans to each other, therefore it is E trans. Okay, so this product is the major product. Now, if the reaction had happened in an anti-Cram model, so if the reaction had happened in an anti-Cram model where if the nucleophile had attacked this carbon from this direction, we would have ended up with a cis product. So that is how we understand this problem, where we try to predict the stereochemistry of the product applying Cram's rule, as well as after the Cram's rule we get the product, and after that we treat that product with further reagents, and finally we end up with this product. Let me take up another problem using Cram's rule. Now in this problem, again we have to predict the product and also the stereochemistry. Let me draw the molecule first. This is my starting material, and I have to predict the product and also need to predict the stereochemistry of the OH group that is going to be formed here, and also with respect to methane. I have to predict the stereochemistry of the OH group formed with respect to methyl. In other words, I have to say whether the relationship between the OH and methyl is cis or trans. Let us take up the Felkinan Cram's model. So according to Cram's model, we are going to draw the Cram's model. As I told you in the previous problem, we are viewing a molecule from this direction. So we are viewing a molecule from this direction, and please remember there is always one hydrogen over here. So there is one hydrogen over here, and therefore we are trying to view the molecule from this side, and therefore we will be having the medium size group in this side, small size group in this side, and we have our larger group here. So this is how it will look. And now when your phenyl group attacks the nucleophile, when the phenyl group attacks the carbonyl, we end up with a product. So we have a product here. And we have our methyl and hydrogen and the larger groups over here. Now this product is actually obtained. So I'll just put up here. The attack takes place on the side of the smaller group as mentioned earlier. So we will have our hydrogen over here, we will have our phenyl here, we will have our medial group over here, we will have a small group over here, and we will have a large group over here. Now we need to predict the stereochemistry of OH formed, and also we have to correlate the stereochemistry of the hydroxyl group form and also the methyl group. Therefore, let us try to draw the product over here. Let me draw the product. So one of the important rule while drawing or while predicting the product is the longest chain and the nucleophile are always anti to each other. So we have our phenyl group here. Therefore, our OH should be somewhere here. So this is our OH, and our methyl is going to be somewhere here. And please remember, we have drawn the longest chain and the phenyl anti to each other. Let us come back to this. Now let us try, so this is equivalent to this, you can see. Now let us try to make the things a little bit easier. We will make a rotation. Okay, so when I make a rotation, say around 60 degrees, my phenyl comes over here, my OH moves here, my hydrogen is here, my methyl is here, and my hydrogen is here, and my large group is here. So you can see my phenyl and my large group are anti to each other. In that case, my methyl on the chiral carbon and my OH are cis to each other. So they are cis to each other. If that is the situation, then what we need to do is we have to make these two groups as cis to each other. So what we will do, we will draw a cis structure. So I have my cis groups over here. So my methyl and OH are cis to each other. Methyl and OH are cis to each other, like how we have found it here. So they are cis to each other. So one has to ensure that whenever we try to find out the product, we have to ensure that the larger group and the incoming nucleophile are placed in such a way that they are trans to each other in the Newman projection, following which we can easily identify the stereochemistry of the product.